equilibrium. Relative equilibrium is a foundational concept in relative gravity that redefines how forces interact over distance and time. Unlike Newton's gravity, which sees force as a simple attraction between two masses, or Einstein's relativity, which views gravity as space-time curvature, relative equilibrium treats force as an ongoing exchange of energy, governed by relative mass, spatial time, and impedance interactions. It took over a year to fully appreciate its depth, and that makes sense because relative equilibrium is not just a new equation, it's an entirely new way of thinking about force, motion, and balance. Below is a discussion of its broad scope of applications, demonstrating its potential to unify gravity, electromagnetism, and cosmic dynamics. 1. Orbital mechanics. A new understanding of planetary motion beyond Kepler and Newton. Classical mechanics treats planetary orbits as elliptical paths dictated by gravity. Relative equilibrium suggests orbits are dynamic balancing acts of alternating force exchanges, where planets and stars exist in a state of mutual relative mass resonance rather than simple attraction. Implications: why planets don't just fall into the sun. Right arrow, they maintain equilibrium through force superposition, not static balance. How orbital shifts occur. Right arrow, relative equilibrium suggests gravitational tidal waves influence motion dynamically, potentially explaining planet migration and chaotic orbital transitions. The role of dark matter as impedance. Right arrow, instead of being a missing mass, dark matter may be a field regulating orbital interactions by governing the exchange of relative force. 2. Galactic structures. Why spiral galaxies maintain their shape. Relative equilibrium as a self-regulating galactic system in classical models. Galaxies should gradually lose their structure due to rotational momentum, yet they remain stable for billions of years. Relative equilibrium suggests galaxies maintain stability through self-regulating mass-distance relationships, where each region of a galaxy operates within a force-balanced framework. Implications: Fibonacci scaling in galactic arms. Right arrow, the logarithmic spiral structure emerges not from gravity alone, but from an equilibrium of radiated forces. Gravitational wave feedback loops. Right arrow, galaxy cores and outer arms may communicate through impedance matching, ensuring relative mass distributions do not collapse or disperse chaotically. Dark matter's role in galactic rotation. Right arrow, instead of adding unseen mass, dark matter may act as an impedance regulator, controlling how mass-energy interactions distribute force over vast distances. 3. Black holes and the energy transfer between mass and space. Black holes as alternating current generators of the universe instead of treating black holes as singularities where mass collapses indefinitely. Relative equilibrium suggests black holes function as mass-energy regulators, where energy is periodically re-emitted through quasar-like resonance bursts. Implications: why black holes emit energy. Quasars. Right arrow, instead of being one-way matter sinks, black holes are part of a relative equilibrium cycle, where mass is redistributed over spatial time through harmonic interactions. Gravitational waves as impedance events. Right arrow, lensing effects near black holes could be governed by impedance variations rather than space-time curvature, leading to new predictions for Hawking radiation and event horizon behaviors. Black hole pairs and superposition states. Right arrow, the interactions between two black holes may form a mutual reference frame, providing a way to study the nature of gravitational wave interactions at cosmological scales. 4. Cosmic expansion and the question of the Big Bang. Relative equilibrium and the evolution of the universe. The standard cosmological model assumes the universe originated from a single explosive event, expanding uniformly in all directions. Relative equilibrium suggests expansion is not a uniform stretching of space-time, but a phase-driven resonance event, meaning different regions of the universe expand at different rates based on force superposition and impedance balance. Implications: why the universe's expansion rate changes. Right arrow, instead of a dark energy mystery, expansion rates could be modulated by relative force distributions, with impedance acting as a feedback mechanism. Multiple expansion events instead of one Big Bang. Right arrow, if the universe expands through a self-balancing process, then the idea of multiple expansion phases instead of a single Big Bang event gains scientific grounding. The cosmic microwave background as a resonance field. Right arrow, instead of being a relic of the Big Bang, the CMB may be a standing wave interaction field caused by equilibrium-driven phase shifts in cosmic evolution. 5. Quantum mechanics and the nature of force interactions unifying gravity with electromagnetism and quantum fields in current physics. Gravity remains separate from quantum mechanics, making a unified field theory difficult to achieve. Relative equilibrium proposes that all forces share the same parent property, relative force, meaning that gravity, electromagnetism, and nuclear forces can all be understood as variations of the same fundamental interactions. Implications: why the weak and strong forces are not actually different right arrow, they may simply be higher energy manifestations of the same relative equilibrium conditions. Photon propagation as a resonance process, right arrow, instead of moving as discrete particles. Photons maintain their structure via equilibrium-driven impedance interactions. Why gravity appears weak compared to other forces, right arrow. If gravity is a function of relative force exchange across spatial time, its apparent weakness is a byproduct of its extended wave interactions rather than an intrinsic property. Final thoughts. Why relative equilibrium matters. Relative equilibrium is not just an alternative to Kepler or Einstein. It is a fundamental rethinking of force interactions at all scales. It explains planetary orbits, galactic structures, black holes, cosmic expansion, and quantum interactions within the same framework, instead of seeing the universe as a chaotic system of forces pulling against one another. Relative equilibrium suggests that nature self-regulates through harmonic interactions, impedance balancing, and force superposition. This is a major paradigm shift. It took over a year to fully grasp the depth of this concept, and now, as we explore its applications, it becomes clear that relative equilibrium may provide the missing link in physics, from unifying force interactions to explaining the structure of the cosmos itself.
Exploring solar system bodies and gravity. When delving into the realm of gravitational waves, the concept of Kepler's center of gravity, or the seesaw analogy, m1d1 equals m2d2, provides valuable insights. This theory posits that space undergoes warping due to the presence of a heavier celestial body, thereby attracting smaller bodies in its gravitational field. Visualizing this phenomenon, particularly through table models or depictions resembling a plane or spatial fabric distorted by a central mass, aids comprehension. One can easily envision a smaller body trailing behind the larger one, while simultaneously experiencing centrifugal force urging it to veer away. This delicate interplay between gravitational attraction and centrifugal force stabilizes the orbit of the smaller body. Furthermore, one can conceive of the spatial fabric itself resonating due to the immense solar mass at its core, potentially amplifying what we perceive as gravity waves. A fresh perspective on gravity. Rather than relying solely on a two-dimensional depiction of warped space, let's consider a three-dimensional model. What if we contemplate space as genuinely warping around solid bodies? In an alternative approach to understanding gravity, let's explore the notion of gravitational fields emanating from celestial bodies, similar to Earth's electromagnetic field. Gravity, being one of the fundamental forces, can be conceptualized as a field surrounding a massive body. Considering fields for gravity. By rearranging Kepler's equation as m1/d2 equals m2/d1, and applying it to the Sun and Earth, intriguing results emerge. Surprisingly, calculations reveal that distance 1 and distance 2 converge at the exosphere level. This convergence point coincides with phenomena like the electromagnetic storm, suggesting a correlation between gravitational fields and observable atmospheric events. Unraveling the mystery of gravity. Contemplating the origin of gravitational fields prompts profound questions. Why do masses exert gravitational pull? To delve deeper, we must consider that matter comprises various forces, including gravity, matter and radiated fields. Viewing matter in terms of potential energy unveils the concept of radiated fields. Just as Earth possesses an electromagnetic field, matter itself can be envisioned as a nexus of energy and time, as per Einstein's E equals m.c. 2. Imagine the Sun and Earth as dynamic masses, each possessing unique gravitational fields resulting from their respective forces. Despite their differences, they exist in a state of relative equilibrium, symbolized by a calculated convergence point above Earth's surface. Speculating on Sun-Earth dynamics. Could the Sun and Earth share a synchronistic state of superposition, characterized by harmonic resonance and frequency modulation of their gravitational fields? Considering the analogy of electrical currents, could gravity itself be akin to a perpetual alternating current flowing between celestial bodies? In this speculative exploration, the Sun and Earth oscillate in perpetual synergy, manifesting as mutual alternating currents at a fundamental frequency, perpetually seeking equilibrium.